Marin has been given the assignment from her boss to test the fatigue strength of this living hinge. Being the hard-working and reliable employee she is, she decides to get right to work and start testing. It appears despite her best efforts, Marin is the one that has become fatigued. We can see from this case study that testing the endurance limit of a sample is not a trivial matter. There exists right now a need in the CMR lab at BYU to test the fatigue strength of a variety of living hinges. The manner in which they need to be tested is described best by the schematic. This drawing represents a living hinge and it can rotate about its center pivot. To test, one end will be fixed to ground while the other angle will be rotated through a prescribed angle of deflection, such as alpha, beta, or even angles that exceed 180 degrees. To assist in this process, there exists currently an electronically driven crank slider mechanism that can be used for a variety of testing purposes. However, there is no way to attach and test living hinges. That is where our kinematic project comes into play. Our solution primarily relies on a rack and pinion approach. The linear motion of the slider is turned into an angular displacement, and different angles can be achieved. And here is our proof of concept prototype that we made, and depending on what hole the crank slider arm is attached to, determines the amount of angular displacement. Previous to building and verifying our prototype, we first analyzed the feasibility of this mechanism using an Excel spreadsheet. By inputting the length of the input crank, we could determine the displacement of the slider and the angular displacement of our test fixture. We could also determine the velocity of the slider as a function of the crank angle, as well as the angular velocity of the fixture and mechanical advantage, both as functions of the crank angle. As you can see, different lengths of the input crank led to significantly different system behavior. From this model, we predicted that we could achieve any angular displacement between 15 and 180 degrees. We then used our prototype to verify that our calculations were correct. We tested small angles, and we tested large angles, and we tested a few angles in between. And sure enough, our kinematic fixture behaved as expected, and we verified it had an angular displacement between 15 and 190 degrees. There you have it. We hope you enjoyed watching.